Okay, and so we'll go ahead and start with those questions. Let me go pull up a screen. And we have some interesting stuff today too. So maybe as we kind of get into these questions, maybe some people will come in and we'll be able to hear all that stuff. But okay, so I know these things, I didn't change it from last time. We went over these last time, so I won't go over them again. Okay, so the last two, I think I said I was specifically gonna not gonna go over that yesterday. So dealing with categorical variables, how do we set the category variable to ordered? Why do we set the category to ordered in the binning process? But then in multiclinarity features, we set the data to unordered. I think I took a look at this last time. So let me just pull up the lesson itself. So, and we're gonna look at the solution since that's probably what we're referring to, right? So. Okay, so as ordered. So the question was, why do we set it to ordered in here? Ordered, all it's going to do is basically going to make it so that we have basically what's the most from top to bottom, which is going to be different from the actual split. I don't actually think there's a reason why you need to have it ordered. There's no specific reason why we would have to do that for the binning process, because these are basically going to be eventually, I think the lab kind of talks about this, is that we're basically saying oh, this is group 1, this is group 2, this is group 3, group 4, right? So it doesn't really matter which group you call which. It might be useful, as ordered, might be useful for you if you have many categories and bins and stuff like this where you might want to see it out. But I don't think it's necessary. Just to kind of double check, I think multiclinarity also has something similar to solution and ordered, right? Yeah, so it says as unordered, but it doesn't really matter because we're just basically saying what are the bins anyway. We have this part and then we're just saying the bins and let's see here, bins rad. Oh, that's the name of the actual operation. Yeah, it doesn't really matter because in the end, all it matters is that you're just saying, oh, this bin is group 1, this bin is group 2 and such. So I don't think there's any specific reason why we would need to keep it ordered, at least in these two cases. I think just maybe someone just wanted to do it differently or show you that there is a possible way to order them. Okay. Any questions or any comments on this guy? No? Pretty clear? Yeah, simple stuff, but just know that you can order it. Why does this is fun. So why does stepwise selection result in a lower R2, so R squared, than the initial model using stats models? Are we getting slightly inferior models, but more interpretable as fewer features? So this is actually a really important point. R squared, by default, well, not just by default, when you add more features to R squared, if you add more features to your model and then calculate R squared, the more features you have, the better the R squared. And the thing about that is subtle, is that it doesn't matter what the features are, because you can think of it even if you put a feature that's completely random, not related to the data set at all, not related to the target, by chance, there's going to be some ability to maybe, predict something by knowing one of these features that's not related at all. And so R squared will always go up. So this is why stepwise selection. So has anyone reached through stepwise selection? Give me a thumbs up if you guys have heard stepwise selection so far. Okay, I see a couple thumbs up, some head shakes. That's okay. So stepwise selection, basically, so when we're doing multiple linear regression, we have all these different features. There's a few reasons why we don't want all these features. Some features might not really be that useful in predicting things. Other times we also might have features that, well, one of the things is the solution to figure out, if you have more features, you have a harder time actually producing the exact answer that best fits the line. We can actually perfectly solve this equation for what the line is, what the best line is for all this data. The problem is it goes up by about n squared, n to the power of 3, which means that if you have 10 more features, then let's say you have 10 features and then you now have 100 features. To compute it, it doesn't take 10 times as long to compute. It takes 10 squared times longer. So it would be 100 times longer. Or if in the cube spot, depending how you implement your linear regression, that would be, what's that, 1,000 times, or yeah, 1,000 times longer. And that can get very significant, especially if you think about one-hot encoding. If we one-hot encode dummy variables, many variables as well, that can increase the number of features to literally hundreds, if not thousands of features. And so that's one reason why you might want to reduce it. There's some ways to get around this. Like gradient descent is one option to kind of help us kind of alleviate like not having to solve it perfectly, but good enough. The other thing is too, is that maybe you don't need all those features. Maybe maybe there's only like the first like 10, maybe you have like thousands of features and maybe the first 100 are perfectly good in basically identifying it. Plus, we'll talk about today, polynomial regression and interactions, is that if you had 100 different features, and each one of those can interact with each other and you want to test all of those things, that's a lot of features to test out. So that's another reason. And then the last part is that, again, R squared is always going to go up whatever feature you put in there. And so we actually use something called, well, one possible solution is using adjusted R squared. Give me a thumbs up if you guys have heard adjusted R squared already. Okay, so good. Most people have heard this, if not everyone. So adjusted R squared, basically, just to remind you, is basically an R squared and then basically punishes it if you have more features. So you have to, basically your feature, if you add a new feature into it, it better be useful in explaining the variance. Otherwise, the adjusted R squared will actually fall down if you add that feature. Okay, and that's the one way to punish it too. There's other solutions too, like for example, later on we'll talk about something called regularization, and regularization is another way to basically punish when you have too many features. Like you can almost think of it like the person who at a sports game, right? Like always wears the same jersey because when they wore that jersey that one time, the team won, and every time they've worn it since, the team's also won. So like they're like, well, I need to wear this jersey. That's kind of the idea. Is like that feature of wearing the jersey or not wearing the jersey is probably unrelated to it, but by pure chance, this, there was a correlation with it. So it's going to be, the model would put that into that as like, it's like, oh, this is useful, and your R squared will go up, but it's just pure chance. So that's why you want to basically reduce the number of features. And also interpretability, I think that's right here. If you have too many features too, and so many interactions, it becomes a more complicated model, which, I mean, depending on the situation, if you're like, this is just basically just to make the best results, it's possible to have a very complicated model and say, I don't know how it works, but it works, which might not be the best thing. But also for your own sake too, for basically communicating this information, it's useful for you to know how some of these things work, and also debugging in a lot of ways too. This kind of goes into a very like general machine learning part. But if you guys remember, like, you guys know about like Apple's new credit card, like you guys have heard about this. I don't know if anyone's had it, but like, people might have heard about this. So Apple has a new like credit card tied to their system and stuff like that. And there was this story I remember like a few months ago when it had just came out. And it was a husband and a wife, and the husband had like a credit limit, let's say, like, I'm just gonna make something up, like $1,000. And the wife's credit limit, they shared income and stuff like that, or shared everything, right? Only had like credit limit, I'm gonna make something up again, like $100, less than him. And they were calling us like, oh, what's going on? And basically, they kind of documented a little bit like what happened. And the service rep basically says that, oh, it's done by machine learning, basically. It says something like a model, like based on our thing. And the thing is, like, they couldn't tell them exactly why his wife, basically had the same exact debt, income, and all that stuff, right, as he did, that she suddenly doesn't have as high of a credit limit. And that's an important part of interpretability. So like you could actually go to someone and say, oh, this is the reason why. Some machine learning models, not linear regression, but other linear machine learning models, literally, like, it's talked about as a black box. You put stuff in and things come out, and it's a lot harder to understand exactly what's going on. So there's another reason why you want to like make sure it's interpretable. But usually the fewer features is more like for us to human wise. You can actually pull out any like of those features and understand how each feature interacts and contributes to the overall prediction. But I don't know, it might help you a little bit if you want to make a simpler model and see like how simple can you make it with still getting good results. It's possible you want fewer features too. Cool. So yeah, this is a pretty loaded one, but any questions or any comments on this section, stepwise selection and R squared?